So now that we've learned about lenses and mirrors, we're going to talk about some interesting optical phenomena, some practical examples of optics. The first is a pinhole camera. Unfortunately, we can't look with this recording at this little YouTube video. But the idea is that if you have a little box, we call it a light-tight box, so a sealed box with a little teeny hole in the center, then the rays of light that are reflecting off a tree, for example, would pass through that hole and would create an image on the back of the box. And if you actually create a light-tight box and you put some film there, you can take a picture of an image. And the idea is you want the box to be really small because then the rays that will come through will create a really tight, well-focused image on the back of the box. So it's called a pinhole camera. Interestingly, if you are having trouble seeing something in the distance, or like maybe some writing on the chalkboard, if you make a little teeny hole with your finger and look through the hole, you'll find that the images come into focus better on the back of your retina. You're losing any of the aberration of the focus of your lenses, and so that light passing straight through will focus on your retina, and you can see it more clearly, so you can try that sometime. Your eyeball acts as a kind of a camera, obviously. It has a lens. This is the lens right in here. You have a lens, and then you also have your cornea up here, which does some refraction as well. So the light will come in, it bends off the cornea, and then it bends more through the lens and refracts on, ideally, the back of the retina. We talked about hyperopia and myopia. But the idea is that, and the image actually that comes through is a real image. It's well outside the focal point of this particular lens. And because it's outside the focal point, the rays come in parallel, they bounce and they come back to the focal point. And the focal point should be hopefully your retina. And the image, therefore, is real and it is inverted. Now it's your brain that takes an upside-down image and converts it to think that it's actually a right-side-up image. So there's some interesting neural processing that happens in taking that image and telling you that it is, in fact, right-side-up. Okay, we're going to talk today about telescopes. There's two types of telescopes we're going to discuss. The first is a refracting telescope. So the key word is refracting, meaning that it's going to be a lens. So we're going to have lenses in a refracting telescope that will take an image that's far in the distance and magnify it so it's easier for us to see. And I have a larger image of this, and so we'll take a look at it again in a second. But this is a typical refracting telescope. It's long and thin and narrow. This is an eyepiece. That's just for sighting what it is you want to look at. And then here's the main eyepiece that allows you to look and see something that's far in the distance. So refracting telescope has two lenses, an objective lens, which is right here, and an eyepiece lens, which is right there. And this is the type of lens that Galileo, he didn't invent it, but then he popularized it, kind of made it simple and cheap, and sold it and made a fortune. Also made himself very famous. Disadvantages of a refracting telescope: because the light is passing through lenses, you have some problems created. You have spherical aberration. We're going to talk in detail about each of these aberrations in a minute. Chromatic aberration. Okay, so chromatic, think color. And then lenses, like typically a glass lens, they can actually change shape over time. The glass it sort of liquefies a little bit, and so those lenses can sag and change shape, and that will cause other aberrations. So when you're looking at the large telescopes that are looking out into outer space, they're not typically refracting telescopes because of these particular problems. So here's a closer look at a refracting telescope. Here is your object here. The light rays are going to come through your objective lens. And as they come through the objective lens, they get focused, forming a real image apparently at their focal point, because this object would assume to be pretty far away. So you have parallel lines coming in. They're going to focus at the focal point. So here's the first focal length for that lens. And so you're going to get an upside-down image right here. And that's a real image. Well, in order to magnify that, then you take a second lens right here. That's your eyepiece lens. It has a shorter focal point. And you put your eye at about the distance of the focal point and equidistant from the image, the real image of your original object. And then your eye is going to take that and it's going to enlarge it significantly. So what you'll end up with is a much larger look at the object you were originally looking at. Now notice that the image you're going to have is inverted. That is an actual virtual image, but it is just taking this is one on each side here, and making it larger. So you have the two lenses. One brings it into the focal point, inverts it, that's a real image, and then you use your eyepiece lens to magnify that and make it look bigger. That's just basically a giant magnifying glass, this eyepiece lens in front here. Okay, let's talk about some of these aberrations we talked about. An ideal lens is going to take all of the rays that are coming in parallel and focus them at a common point, at a single point. But a real lens is only going to take the light that is coming towards the center of the principal axis and focus it really sharply. And the outer rays are going to be refracted slightly differently, and so they're not going to intersect at the exact point. So the rays of your outer edge bent more than those in the middle. And that's going to cause some blurriness. We call that spherical aberration. And you could overcome that with parabolic types of lenses, but once again, parabolic lenses are very expensive to produce. So we tend to create the spherical ones and then essentially just eliminate the light that comes from the outer areas, and that way we can minimize the effect of the spherical aberration. A spherical aberration, an aplanatic point, the point where there's no spherical aberration, is only at a radius that equals the radius of the sphere divided by the index of refraction of the lens material. So typically for glass, which is about 1.5 of an index of refraction, about 43% of the area, so 67% of its diameter. So, something like this. Only this much area is actually going to be giving you a useful image. Otherwise, the rest is, you kind of want to cut it out because it's going to cause a blurriness. Okay, chromatic aberration. Chrome, think like Kodachrome. That's the slide film that we used to use back when we didn't have digital photography. So chromatic means color. So chromatic aberration is what we're going to get with a lens as well. Now, when we were studying refraction, especially in the lab, we noticed that blue light bent more than red light. That blue light actually goes slower through glass or through plastic than red light does, so it gets bent more. So the problem there is that if you're going to pass white light through a lens, coming here, coming here, coming here, the blue light frequencies are going to bend more than the red light frequencies are. And so you're not going to get a crystal clear image at your focal point, because the focal points are going to vary depending on which frequency of light you're talking about. So this picture over here is not a great example, but it does show some chromatic aberration. Again, chromatic aberration is something you're going to get when you're dealing with lenses, not with mirrors, right? Because when you're doing mirrors, you get reflections. You don't get that varying refractive index that's going to change one color light bending over another. You can correct chromatic aberration if you have a converging lens and you get that blue light bending more. You can put a diverging lens in front of it, and that will cause it to realign. But you have to be really particular about those two lenses lining up exactly to get the blue and the right to line up precisely at the focal point. But it can be done. Okay, so let's look now at a reflecting telescope. Okay, reflecting. The other one was a refracting. It was long and narrow, had two lenses. This is a reflecting telescope. This one is actually much more common, especially in large observatories. The idea is you're going to get mirrors to gather light and then reflect to form an image. So you're going to start with an image reflecting your eyepiece lens or series of lenses. So here it goes. Your light comes in. You have a primary mirror back here. It could be spherical or it could be parabolic if you can afford it. And you have light coming in, and that's going to bounce off. And then you put a mirror over here, and that will cause the light to bounce and invert, and then you hit a lens. So there is a little lens as part of your reflecting telescope. The image, again, so if you dial in closely, the image is going to be right here where your focal point is. There's your image. And then the eyepiece is going to allow you to pick up that image through the lens and basically see a magnified version of what you're seeing out in outer space. So more astronomical research telescopes are these reflectorized types. They can get more light coming in, and that is that's half the battle, is getting enough light so that you can view something that's far in the distance. And you also will eliminate chromatic aberration because you're dealing with mirrors. You're not doing any refracting, so you won't bend light differently. Isaac Newton built the first one, but it ended up being very difficult to produce, so not often would we create these until we got better at engineering them, basically. The Hubble telescope, the world-famous Hubble, is out in outer space. It was launched back in 1990. It's called a Cassegrain reflector telescope. The idea of the Hubble was to get it up in outer space and beyond the particulate matter of the atmosphere, because light coming in through the atmosphere is going to be warped. It's going to be fuzzy. So you want to get up above the atmosphere, and then you get super clear pictures. So the Hubble was launched with the help of the space shuttle. It's in orbit 350 miles above the surface of the Earth, and we can eliminate all of the atmospheric distortion and filtering. It has been enormously successful in advancing the study of astronomy and physics and dark energy and matter, giving us a much clearer understanding of the age of the universe, among many, many things. So it has, I think I read 50,000 papers have been written based on studies and observations done from the Hubble telescope. And again, the idea is this is a reflecting telescope. Light comes in through here, bounces off a primary mirror to a secondary mirror, and then comes in here where there's all kinds of cameras, several different types of instruments that are designed to study different wavelengths of light. Some are infrared, some are ultraviolet, some are visible light. So each of these instruments is designed to interpret the data that comes through. Interesting, when they first launched the Hubble, it was the images were slightly fuzzy, and they were just distraught because they'd worked so hard to engineer this thing. It turned out they had a problem with spherical aberration, and they said the thickness of the anomaly was 1/50th of the width of a piece of paper. That's how far off they were. So they ended up inventing and creating a series of mirrors that would slightly alter the light that came through for the instrumentation. They called it COSTAR, and it's an acronym for something I don't remember. But once they brought the COSTAR up on another space shuttle mission, went into the Hubble and repaired it, that it has been able to give us these spectacular images. The Hubble telescope has undergone several upgrades throughout the years. The last one was in 2009. So the shuttle, often the shuttle was, its purpose was to go up and fix and repair the Hubble. It's coming to the end of its life expectancy now. 2013 was what its expected life ending. I think it's continuing to work. I don't know exactly how long it's going to last. They were originally thinking that they were going to bring it back on a space shuttle and put it in a museum, but now that the space shuttles have all been decommissioned, it looks like the Hubble is just going to be out there until its orbit eventually decays and it crashes back to the Earth, which is kind of sad. They are in the works producing a newer, more advanced telescope that they're going to launch and put in much deeper space, much higher than 350 miles, again, to try to get those sort of incredible images that we've seen from the Hubble, except at an even higher level, advancing the study of physics. And that concludes our lecture for today.